Last lesson, we have been talking about the simple harmonic motion. So we repeated some of the discussions concerning the simple harmonic motion. As I stress from time to time, the important point about the simple harmonic motion is that it forms the basis for many kinds of the oscillation behavior. All of the oscillations in mathematics can be represented as a sum of sine or cosine functions of different frequencies, and that is called a Fourier analysis. This would be a topic you would learn maybe in the second or the third year of the mathematics. So for the simplest case, we would be analyzing the behavior of objects that are oscillating in a sine or cosine manner as a function of time. And for systems performing this type of oscillations, they are known as performing the simple harmonic motion. When a system performs a simple harmonic motion, there would be a very characteristic behavior, namely that the acceleration of the object is related to the displacement of the object from the equilibrium position. So we have this equation. Basically, you start by observing that the acceleration is proportional to the displacement of the particle from the equilibrium position. And in order to perform an oscillation, the acceleration must be negative to the displacement. Otherwise, when you have a positive acceleration with positive displacement, the objects would just accelerate away from the equilibrium position. Only when you have the A proportional to minus x, then the acceleration would try to bring the object backward when the displacement is into the positive x direction. Similarly, you have positive A when you have negative x. This again brings the object back to the equilibrium point. But because of the inertia, the object would overshoot the equilibrium and it keeps on oscillating. So this would be the defining equation, if you like, for simple harmonic motion. Acceleration is proportional to minus displacement. Of course, it can be angular acceleration, in which case the displacement is the angular displacement. This would be the situation of the simple pendulum. We have looked into two specific situations of simple harmonic motion. One is the spring mass system, when you connect a spring to a mass. So the spring provides the restoring force, where the mass of the object would be responsible for the inertia. And secondly, we have discussed the case of the simple pendulum, where you have a bob or a mass connected to a string. Here, the restoring force is provided by the tangential component of the weight, tangential component of the weight for the angular motion. So you have this force, mg sine theta, that is responsible for the restoring force. And the inertia is due to the object always trying to return to the equilibrium position whenever it is displaced by an angle theta from the vertical location. So This would be the case of the simple harmonic motion in the simple pendulum. And when we derive the equation for the simple pendulum, we assume that angle is small. With this assumption, we could have a approximation sine theta that is close to theta. And therefore, the second order derivative of the theta with respect to time, that is the acceleration, would be proportional to minus theta. That is how we declare the simple harmonic, the simple pendulum is performing simple harmonic motion, because once again, d squared theta over dt squared, acceleration is proportional to the displacement, and it is in a negative sense. The omega squared term, which is the positive constant term in front of the theta, would be related to the angular frequency. Omega is equal to 2 pi f. So this would come naturally as the oscillating frequency of your system. And in the second part of our last lesson, we talk about the case of the sound wave. Of course, some of the properties we expect you to know. The sound by itself is a medium wave. So you need to have a medium for the transmission of the sound. Either it is fluid, for example, gas, or solid. And for human ear, the hearing range is between 20 to 20,000 hertz. Any sound below the frequency of 20 hertz would not be heard by the human ear. And that is what we call the infrasound. And sound with frequency above 20,000 hertz, it would be regarded as ultrasound. They have their uses, but they cannot be heard by the human ear. And just as a quick revision in the last lesson, the sound comprises of the regions where you have a high density of air particles or medium particles, and they are called compression. And there are also regions where there is a slightly lower density of the particles, and that would be the region of the rarefaction. So it is the continuous generation of the compression and rarefactions that permits the transmission of the sound wave. Speed of the sound. Here we just mention it as a knowledge, if you like. The speed of the sound is related to the temperature of the medium. So it is related to the temperature of the air, for example. For the case of air, the equation is highlighted in the slide. Exactly how this equation is derived, that is certainly beyond our level of teaching, but it is actually related to the absolute temperature, if you like. So that is the equation for the speed of the sound in the air. An important topic in the chapter 17 is the Doppler effect. We have spent some time in the last lesson talking about the occurrence of the Doppler effect. Basically, you have, well, in order to detect the sound, you need to have a source and a receiver. If there is a relative motion between the sound source and the receiver, then there would be a corresponding change in the observed frequency of the sound. And this effect is called the Doppler effect. In the video that I showed you last time, we have the car, which is the source, because it is making a the hooting. It makes the horn that is blowing all the time, so it gives out sound of a certain frequency. As the source is moving towards the receiver, the frequency is higher. And as it is moving away from the receiver, the frequency is lower. Although the sound source is generating the sound at a specific frequency, the apparent frequency detected by the observer has changed. I'm not sure if this video link actually shows anything. Maybe not. So the idea actually has been shown quite clearly in the video last time. In particular, in the last lesson, we derived the equation for the Doppler effect with the source moving, with only the source moving. The reason why we have a change of the observed frequency can be understood as this. In the case of stationary source, sound wave would be emitted equally in all directions, kind of like the diagram shown below. Now, what the diagram shows here is the diagram of wavefronts. You could understand the wavefronts to be the crest or the maximum point of your particle displacement. So here, if you have a sound if you have a sound source emitting sound of constant frequency. So if the frequency is constant, the wavelength should be constant. That means the distance between adjacent wavefronts, they are all equal and they are all separated by the distance lambda. Well, that is the idea of one wavelength, which occurs after one single period of oscillation. So if you have the source that is not moving, the wavefronts would be spreading out in the shape of spheres. And each sphere is separated from the adjacent spheres by a distance of lambda. Of course, we are looking in a two-dimensional way, so we are looking at some circles. Now, if your source is moving, then from time to time, the source would be moving. For example, in the diagram on the top, it will be moving from left to right. So the circles are no longer concentric. They are no longer sharing the same center. For example, the outermost sphere, the outermost circle would have the center at here. But then the circle, after a period of time t, and that is the one adjacent to it, would have the center move by a distance delta lambda. This delta lambda is equal to the speed of the source multiplied by the period of the oscillation. Remember, adjacent wavefronts are separated in time by one period of oscillation. After all, these wavefronts correspond to the peaks of the wave. So they are separated usually by one wavelength, and that corresponds to a time of t, one period of oscillation. So if the source is moving with a speed vs, then the center of the circles would be moving at a speed vs. And the distance between adjacent circles have the center that is moved by distance delta lambda, which is equal to vs times t. Therefore, the new wavelength lambda dash would be equal to the original wavelength lambda minus delta lambda. That is on the side of observer A, where the source is moving towards observer A. Of course, on the side of observer B, where the source is moving away, it would be lambda plus delta lambda. Delta lambda, as I just explained, would be equal to Vs times T. So we could write down what is the new apparent wavelength for observer A and observer B. The apparent frequency can then be calculated as V divided by lambda dash. So you have the equation for the source approaching observer and the source moving away from the observer as the equation at the top and the equation at the bottom. As you can see, the equation is having a correction factor V over V minus Vs or V over V plus Vs, depending on whether the source is moving to the observer or moving away from the observer. So you could simplify, in a certain sense, you could simplify the equation by writing something like this: V over V minus plus Vs times F, where F is the original source frequency. V is the speed of sound. Vs is the speed of the source. Minus sign here correspond to the source approaching observer. Plus sign means the source moving away from observer. Well, it's always difficult to remember equations, but if you think about it, when the source is moving towards you, frequency should increase, and you would recognize that you have to use the minus sign in that case. On the other hand, when the source moves away from you, the apparent frequency should be reduced. So we use the plus sign. That is, in a certain sense, helping you to remember the use of the equation. Okay, we talk about the source moving. What about source stationary, but the observer moving? For the case of observer moving, it would be not any change of wavelength. It would be the change of the relative speed of the sound that brings about a frequency change. Think about it. If you have the source that is stationary, the wavefronts would be distributed like the diagram on the right-hand side. Wavelengths are kept as the same as it should be. So there would not be any change of the wavelength. On the other hand, if you have the observer moving, then the relative speed of the sound to the observer would be changed. If the observer is stationary, the speed of the sound should be V. But if the observer is moving towards the source, the apparent speed of the sound would become V plus V naught. It seems that the sound is traveling faster, if you like. On the other hand, if the source is moving away from the observer, if the observer is moving away from the source, sorry, I just write down here first. Observer moving to source. On the other hand, if the observer is moving away from source, it would have a new apparent speed of the sound, which is V minus V naught. Observer move away from source. Then there would be a new apparent speed of the sound, V minus V naught. The sound seems to be slower because it would be a longer time before the same wavefront can catch up with the observer. So the wavelength has not changed, speed of sound has changed. Therefore, the apparent frequency would be changed. Here on the top, you have the observer moving to the source. Observer, sorry, maybe I put it this way. Observer approaching the source. Then the apparent frequency would be V plus V naught over V times F. And similarly, if the observer moves away from source, then the apparent frequency would be V minus V naught over V times F. We could summarize the two equations as F dash equals to V plus minus V naught over V times F, where plus sign is used when the observer is moving to the source. Minus sign is used when the observer is moving away from the source. So we have altogether 4 scenarios, 2 for observer moving, 2 for source moving. Altogether, we could have a very compact form of the equation, which may or may not be useful, depending on whether you could recognize when to use which sign. But at least the symbols would hint to use something. First, on the top, you have V plus or minus V naught. V naught or VO is the speed of the observer. That means the case of observer moving. On the bottom, V plus, minus or plus VS. VS means the speed of the source. So source moving. If both of them are moving, then you would use the corresponding speeds of the VO or VS. When we use the plus or minus sign, it depends on whether the source is approaching the receiver or whether the receiver is approaching the source. Upper signs in the equation, that means plus sign at the top or minus sign at the bottom. Upper signs of the equation would be for observer or the source approaching each other. Lower signs are for the case when they are trying to move away. So if one is moving away and the other one is approaching, then you have to be careful which one is moving away, which one is approaching. So this is a very general equation, and you have to exercise your judgment based on the source or observer moving and whether they are moving away or towards each other in order to use the correct sign and substituting the numbers either at the top or the bottom of the equation. Here, just a bit of a caution. The important point here is that although we introduce the Doppler effect for the sound wave, in fact, it is present in all kinds of waves. As I mentioned at the beginning, Doppler effect can also be observed in the case of the light wave or electromagnetic waves in general. Although the situation is slightly more complicated, you may need to have some corrections due to the special relativity, because light is traveling at the speed of, well, light. And any change in the frequency or the wavelength would involve somehow the concept of relativity. So the equation may not be as straightforward as in the case of the sound wave. In the sound wave, we use the Newtonian mechanics But then in the case of light wave, because it travels at high speed, close to the, well, at the speed of light, so there would be corrections due to relativity. And the Doppler effect does not depend on the distance. So that is an important concept to know as well. Yes, that is the red shift and the blue shift, which I do not intend to touch upon at here. That is well beyond our syllabus. So here we just have a case of the Doppler effect with both the source and the observer moving. So here you have two submarines, and let us assume that they are moving in a head-on direction, but just that they are not going to have collision. So you have a submarine A being the source, submarine B being the observer. At the beginning, they are approaching one another. So you would be using the equation V plus V naught on over V minus Vs, where you put the speed to be positive for, well, for this example, the textbook assumes that when the source and the receiver are approaching one another, they would be using positive speeds. So they would stick to the positive side at the top, negative side at the bottom, and they would be correspond to the general situation. If you are having the source and the observer approaching one another, then the speed would be positive. And that is the case of A. And therefore, we could see that a corresponding increase in the observed sound frequency. And then in the part B, the situation has slightly changed, where you have the submarines happens to pass through one another. And in that situation, you would have the speed that is changed from positive to negative because they are moving away from one another. The source is moving away from the observer, and the observer is moving away from the source. So that is why we have the negative speeds in the two items, V naught and Vs, where we would keep the positive sign at the top and the negative sign at the bottom. So that is how the textbook deal with the situation. Okay. So this is just a simple demonstration of the effect. Now, in your lecture notes, we have one small slide that discusses the situation when we have not covered in the equation. And that is the situation if the source is moving very, very, very fast, such that it is above the speed of sound. So if the speed of sound is lower than the speed of the source, then of course the observed frequency will be negative, which is physically impossible. In that situation, you would enter into something called the supersonic scenario, and it would come along with the phenomenon called a sonic boom. So rather than having the circles like the one at here, for example, you would have one side of the waves that are compressed and the other side that is further away from each other. In the case where the source is faster than the speed of sound, you would be compressing some wavefronts all together and generate a cone of waves like the one shown at the top. So this is the case of the sonic boom. Now, when you have a sonic boom, it would be quite a different scenario for the observation of the sound. And here, I would just show you the video on your PowerPoint slide or on your PDF file by showing you the corresponding YouTube video. Okay. I don't know if you will see the video. Okay, right. It's a bit loud, I must say. Now, there's nothing to be heard now, but then the sound is just like and it is called a boom for a reason, because it is just like an explosion. All the sound, if you go back to the slide, all the wavefronts at here are kind of like coming together onto a single line. And this single line contains all the sound energy from various sound waves. So that would be a very loud, explosive sound that is come out. And if you check the video just then, you will see that when the airplane is flying at the speed higher than the sound, you see it is always surrounded by a cloud, by some kind of a cloud-shaped structures. In fact, it is related to the heat transfer or thermodynamics, if you like. It generates a region where it would condense all the water suddenly. So that would be a cloud-like structures. Of course, that is well beyond our current level of study. So I just mentioned it briefly here that when you have the speed of sound that is smaller than the source speed, then you would have the shock wave. And this is another big topic of the sound wave, but we will not be touching it at here in details. In fact, if you want to see this type of a situation where the speed of source is higher than the speed of the wave, you could see it very easily. You just go to the sea. You take a look at the ships moving on the water, and all the time you would be seeing the ship making a blow-like structure for the water wave. And that is a simple version of the shock wave, where you have the source that is moving faster than the water waves. So this is a daily live situation. Now, some of your classmates are asking if the equations would be given in the examination. They would be released before the examination. So for the Doppler effect, the equation should be given. And another classmate is asking if I could shift the observer and the source. I'm not quite sure what is meant by the shifting observer and the source. Basically, you could move both of them together and you still apply the same equation. Right. I would take the time remaining in the class by working at one tutorial question. So we will be going to the tutorial set number 4. And let's take a look at question number 7. So here you would be combining the simple harmonic motion with the Doppler effect. And the situation, of course, is a very artificial one. I don't think you will have it in your daily life. Here you have a spring mass system where the spring is connected to the loudspeaker. And so the loudspeaker would basically be the mass. And by putting the loudspeaker on a smooth table and you set the loudspeaker in the oscillation, it will be performing a simple harmonic motion. Therefore, the speed of the loudspeaker changes from time to time. And there would be a corresponding change in the frequency of the sound as detected by the observer. So here you would be having the source that is moving. The source is moving from time to time. So there is a Vs. Sometimes it would be moving towards the observer. Sometimes it is moving away from the observer. Now, let us try to take a look at the question. First, you would be asked to determine the highest frequency heard by the person to the right of the speaker. We would first determine the maximum speed of the loudspeaker. The maximum speed of the loudspeaker can be determined by the conservation of energy because it is a simple harmonic motion. So the maximum potential energy, 1/2 Ka squared, it will be equal to 1/2 mv squared. Or if you like, 1/2 mvs squared. Or actually, maybe better if I put it as a maximum, because Vs is actually a function of time. It changes from time to time, but the maximum speed is a constant value. The value of K corresponds to the spring constant. A corresponds to the amplitude of the motion. Mass M is the mass of the loudspeaker because it is a simple harmonic motion. So in this way, you know what is Vmax. The corresponding frequency, maximum frequency, would be when the source is approaching the observer at the highest speed. Remember what is the equation to be used when the source is moving. Go back to the lecture notes, page 52. The equation for the source moving is V over V minus V max multiplied by F. Of course, the minimum frequency would be V over V plus V max multiplied by F. V max is given at the top. V max, it is equal to A times square root K over M. So you determine the equation in this way. And in the part B, the lowest frequency is also determined in a similar way. Minimum, it would be V over V plus V max multiplied by F. So here you have to recognize several things in order to solve the problem. Firstly, you have to recognize that the loudspeaker and the spring forms the spring mass system, and it performs simple harmonic motion. Then you decide what is the maximum velocity of the loudspeaker by considering the energy conservation. So that is the equation at the top. Once you know the maximum speed of the loudspeaker, you could determine what is the maximum frequency to be detected by the observer and the minimum frequency. Why we could use the same maximum speed? Think about it. Think about it. When the loudspeaker is oscillating, what is the speed? What is the velocity? At the maximum displacement, A, the loudspeaker should be stationary. And then at the equilibrium point, the loudspeaker should be having the maximum speed. It can be moving backward, or it can be moving forward. The velocity or the direction can be different, but the maximum speed is the same when it comes passing the equilibrium point. Similarly, at the maximum negative displacement, the speed is 0. So we have to recognize the physical situation. The box is oscillating. At the equilibrium point, it will be moving with maximum speed, either forward or backward. And at that point, we determine the maximum frequency of the sound because the speed of the source would be highest, either moving forward or backward. Right. And in the question 8, the situation would be actually quite similar. You have the source that is initially moving towards you, is an ambulance, initially moving towards you, and then later leaving you. So the frequency of the sound changes. And therefore, by comparing the sound frequencies in the two situations, you know what is the speed of the ambulance. And here, of course, we have to use the speed of sound, which, if it is required, it should be given to you. So the speed of sound in the air is 343 meters per second. And it should be available in the lecture notes as well. Now, just before the end of the lesson, I would have to make a clear announcement. Let me see. And this is an important announcement. Right. Now, on Learn at PolyU, I have posted a very important message, and I put it in the content page. It would be the first message you will see, and that is related to actually the examination arrangement. You would have received the date of the examination from AR already by email. Because of the accreditation requirement for the engineering departments, students would be required to take examination. And this examination would be an invigilated examination, meaning that you would be supervised by staff or teaching assistants during the examination. According to the announcement of the university management, students in Hong Kong would be required to take the examination on campus. Of course, we would have sufficient health security measures in order to protect the students. For example, we would measure the temperature of the students, and we would require the students to sit at a safe distance away from each other. The concern here would be students not in Hong Kong. As announced by PolyU in September, students outside Hong Kong, we would make suitable arrangements for them. And that basically is online invigilated examination, meaning that students would be invigilated online. And this would be for students outside Hong Kong. So there would be two batches of students. Students in Hong Kong, you would be taking the examination on PolyU campus. Students outside Hong Kong, you do not need to come back, and you will be doing the examination online. And we would require you to show up your face and show up your scripts, etc. during the examination. Details of the online examination would be announced to you later. So what we would like you to do now is make use of 1 minute. Click in this declaration. You first read the whole passage, and at the end, you will be asked to declare your current location. Whether you are in Hong Kong or outside Hong Kong. If you are outside Hong Kong, we would make corresponding arrangements for online invigilated examinations. If you are in Hong Kong, you would be taking the examination in PolyU campus. Please be alerted that online invigilated examination would require quite a lots of preparations. It requires several devices for viewing your face, for scanning the exam paper, and for viewing the exam questions. So it would require you some time for the preparation, and we would need to take rehearsals. For on-campus examination, that is straightforward. You just come, and all the things are done in the usual way. So please take 1 minute, basically, to tell us whether you are in Hong Kong or outside Hong Kong. We might ask you to provide some support. For example, some documents to suggest whether you are not in Hong Kong with reasonable justification, if necessary. Okay. So it would not take you long. And if you are not in Hong Kong now, you do not need to rush back. You just stay at where you are. And this would be the arrangement for the examination in December. I think it is the 15th of December. Okay. So this would not take you long. And if you do not want to fill it now, you have until this Wednesday to complete the question. They are exactly the same question paper. So would not be any difference in the question paper. So the examination would be done in exactly the same time for all the students. Okay, so you just take 1 minute to tell us where you are so we could make the arrangements. If you do not fill in, we would automatically assume you are in Hong Kong, regardless of your name, regardless of how we spell the name, because we cannot check one by one to see who is in Hong Kong, who is not. So you have to tell us. It takes you 1 minute to complete the question. Okay, so if you have any problems or questions to ask, please ask in the consultation hour or by email. Or otherwise, we would be stopping the lesson at here. Okay, so thank you very much.